Hello everyone. My name is Ronald Ssembatya from Makerere University. Here we have a problem in linear programming where the doctor wants to combine two food kinds such that he gets a mixture that contains two types of foods, which is food 1 and food 2, containing vitamins A and C. So here we have a condition whereby vitamin A has to be with minimum requirement of 8 elements, and vitamin C should have minimum requirements of 10 elements. Now, food 1, they're telling us it includes 2 vitamin A units per kilogram and 1 unit of vitamin C per kilogram. Then food 2 has 1 unit of vitamin A per kilogram, and then 2 units of vitamin C per kilogram. So they have given us the price of food 1, which is $5 US per kilogram, and 7 for food 2. Then we need to optimize the price of this combination, or we need to minimize the cost of these vitamin mixtures of food 1 and food 2. So what are the optimal values that will minimize the cost of mixing these two food types? So to answer this question, first of all, we need to know what are the decision variables. In this aspect, the decision variables are the quantities of the food 1 and food 2, because these are the quantities we need to optimize to give us, or to reduce on the cost that we shall be incurring. So as we said, the decision variable is decision variables we have food 1, which we can call, or we can calculate x be food 1 definitely in the kilograms, comma y can be or can represent food 2 this aspect. So these are our decision variables. Well, the quantities we need to minimize the cost. So in this aspect, what will be our objective function? The objective function will be to minimize the cost. So in this aspect, we shall minimize the cost. So what will be the cost? The cost, we shall get it from the by multiplying the units of food 1 and the units of food 2 with their unit prices to get the total cost that we shall be incurring. So it will be the price per kilogram of food 1 times the price per kilogram of food 2, which is y, which will give us the total cost, because total cost will be the product of the unit, the price of each input times the unit of inputs employed. So in this aspect, it will be 5 times the corresponding unit, because 5 is the price for food 1, and we said x should represent food 1, shall say 5x. Then we shall add the 7y, and so this equation should give us the total cost, which we need to minimize. Yes, which we need to minimize for us to be able to get the mixture we want, that you can the doctor can design for this particular case. So this is the objective function, but still we have some limitation, or the constraints. So in this aspect, the constraints will be in terms of the quantity of the mixtures. For example, you have vitamin A and vitamin C, which should contain in food 1 and food 2. So we shall first have the vitamin A constraint. Vitamin A constraint, what would be the constraint? Remember, they told us that the mixture of vitamin content includes a minimum of 8 elements of vitamin A and 10 elements of vitamin C. So the content of vitamin A, the content of food 1, the content of vitamin A in summation must not exceed 8 elements. And remember, vitamin A is contained in both food 1 and food 2. So in this aspect, we shall get the units of food A the units of vitamin A in food 1, which is the 2, and also the content of vitamin A in food 2. So if we get the 2 for vitamin A in food 1, remember food 1 is represented by X, then, and we also add on the 1 unit, this 1 unit of vitamin A in food 2, which is represented by 1. If I say 1Y, it is the same as Y. This one must be, if they say a minimum of 8, it means it must be less than or equal to 8. So we shall insert a symbol here, which is the greater than or equal to. So in this aspect, to be greater than or equal to, because we have to minimize these costs and to minimize the cost. And so they are telling us that the total of vitamin A must be of a minimum of 8. Minimum means it should be greater than or equal to 80 elements. This aspect. Also have a constraint on the vitamin B. So this aspect, the vitamin B constraint. In this aspect, remember they told us that vitamin B should have a minimum of 10 elements, meaning if you add all the vitamin C's, this is vitamin C. If you add a total of all vitamin C's in food 1 and food 2, should give you 10 units. So what are the ingredient in food 1 in terms of vitamin C? They told us 1 unit, and in the food 2 it is 2 units. So we shall say it is 1 unit of X, which is X, plus 2 units of Y, 2 units of Y, which also must be greater than or equal to. So we shall insert a symbol here. Okay, must be greater than or equal to 10. This aspect. We also have the non-negativity constraint. Non-negativity constraint. Non-negativity constraint simply means that these quantities, because you cannot mix 0 quantities of food 1 and 0 quantities of food 2. So meaning our X, or the quantity of food 1, should also be greater than, let me just copy this, should also be greater than or equal to 0, and also our Y should also be greater than or equal to 0. So that is the non-negativity constraint we do have at hand. So after setting our problem that we need to minimize the objective function subject to the constraints, which is the vitamin A constraint and vitamin C plus the non-negativity constraints, we can easily go and use either software. You can optimize, or you can solve this problem using Excel solver. You can use the solver plugin and solve this problem, or you can use it a graph to solve this particular problem. So in this video, we are going to use a graph to solve this particular problem. Here let us use a new slide to easily solve our problem here using a graph. Okay, let me pull this a little bit. Okay. Can reduce on this. Can reduce a little bit. Can reduce a little bit. So this is our problem. So we are going to solve. Using a graph. This aspect. How can you solve this problem using a graph? First of all, we need to put our focus on our constraints, because this objective of minimizing the cost will come for will come after we have gotten the feasible region and the feasible points. So the feasible points we shall substitute in that objective function to know which of those values that are giving us minimum cost. So in this aspect, before drawing a graph, we shall concentrate more on the constraint, and we see what are we get the coordinates that we shall plot on our graph. So let us start with the vitamin A constraint. In the vitamin A constraint, how can you start with this? First, deal with the case where x is 0 and y is equal to 0. But also, the first thing is to change these into inequalities, because you cannot solve this when you have an inequality. You have to first change it into equality, and then solve for these values of x and y. So, if x is equal to 0, what will happen? If x is equal to 0, y, in this aspect, will be equal to 8. Because if you put a 0 here, this will disappear and y will be equal to 8. So the coordinate corresponding to this will be 0 and 8. Because 0 represents x and y, 8 represents y. So if y now is equal to 0, what happens? If y is equal to 0 in the same equation, if you put a 0 here, you remain with the 2x is equal to 8. If you divide both sides by 2, this 2 you get 4. So our y will be equal to 4. So what will be the coordinates we shall have? We shall have a 4, which is, we are looking for, y is 0, but we are looking for x. Our x will be equal to 4. So in this aspect, our y is 0, because we said if y is 0 and x in this aspect, if it is 0 here, x will be equal to 4. So we shall have a coordinate as 0, 4. So those are the coordinates we shall use to plot this equation, our graph. So the inequality will come in if when we are shading the feasible region, or if we are identifying the feasible region. So we shall use the inequality side, don't worry. Then if you go to the vitamin C constraint and bring it here, also we shall use the same format. If x is equal to 0, what happens to our y? If x is equal to 0, we shall remain with, first change this to equality, our y will be equal to 2y is equal to 10 divided by 2, you get 5. So our y is equal to, our y will be equal to 5. So what will be the optimal values here? Those are the coordinates we shall use. We shall use the 0 and the 5, because now x is 0 and y is 5. Now what if now y is equal to 0? What happens? If y is equal to 0, our x will be directly equal to 10. Our x will be equal to 10. So the corresponding coordinates here will be equal to 10 and 0, because our y is 0. Also, the non-negativity constraint here can also give us, we can get points from it, coordinates, because if we put equality here, it shall be x is equal to 0 and also y is equal to 0. Alright, y is also equal to 0. So having the coordinates, we can easily plot and draw our graph. So in drawing a graph, we shall simply go and use a ruler. We can use a ruler, bring it here. Okay. Using a ruler, rotate it a little bit. Okay. So we shall draw. Let me use black. We shall draw our line. The y-axis. Also, we shall rotate. Okay. Also use a ruler, but rotate it a little bit. Okay. Okay, I think we can just draw straight away with our x-axis here. This ruler will disturb us a little bit. Okay, we can use our imaginary values, that are our coordinates we have obtained. This can be our 0. This is the x-axis. This is our y-axis. Now, we have coordinates 0 to 8. This is 0 x-axis and 8 y-axis. Maybe somewhere here. And also, we have for 0, meaning it will be something like this, whereby this is our 8, and then this is our 4. Because this is 0, 8, and then 4, 0. That is the point. So this line, which we have just drawn, we can call it is the 2x plus y, which will give us our 8. But remember, in the original constraint, it was less than, that are greater than or equal to 0. So we need values which are either equal to this line or greater than, meaning we shall shade out this side. We shall eliminate it, because all these values below this line will be less than, and remember our condition is greater than. That is one. Then also we have a point here, 0, 5 on this second constraint. 0, 5, 5 can be somewhere here, and then 10. So it can be something like this. You can call this 10, and you can call this 5. But remember the condition was, so this line we can call it, or it is x plus 2y, 2y to be equaling to 10 in this aspect. So according to the original condition, any points that are below this line would be less than, but the condition is greater than or equal to 10, meaning all these values that are below this line will not be preferable, so will not be under the feasible region. So this side is eliminated. But we have also the non-negativity constraint, whereby x is equal to 0. When the x is equal to 0, meaning it is this line of y-axis. So on the y-axis, this side, also x is equal to 0, because the condition originally was also must be greater than. So this side is less than, so it's greater than. So this point is also x is greater than or is equal to 0. And also y is equal to 0, it is this line down here. Y is equaling to 0. Okay, what will be the feasible region? The feasible region is this area above these two graphs, above these two lines. It is all these spaces contains of feasible points. So the feasible points, like to get the optimum values, we shall have different sets of optimum values. We have this one, we have this, can call this one the slope, that at the intercept, can call this point A, can call this point B, and we can call this point C, where at the x-axis here. So these 3 points will give us the optimum values, but now we need to know which of those 3 will give us 2 coordinates of y and x that will optimize our objective function. Now after identifying, we need to know the coordinates corresponding to A and B and C. Now when you look at point A is clear, because we have at this point it was 0, 8, 0 on the x-axis and 8 on the y-axis, 0 of x and 8 of y. Then point B, we don't have it, or we don't have the coordinates, because at this point we don't know which is the value of x and which is the value of y. But when you look at this point B, it's the point where the first line or the first constraint is meeting the second constraint. So meaning we can get these points by solving these two lines simultaneously. So how can we do that? We can have the first line 2x plus y is equal to 8 is equaling to 8, meaning we can make y the subject. Y is equal to 8 minus 2 to y. So we can substitute it in substitute in x plus 2y is equal to 10. I'm simply using substitution to solve these two simultaneous equations. So our x plus 2 into, remember our y is now 8 minus 2y to be equaling to 10. So from here we can simply come this side and say our x plus, if you open the bracket here, 2 times 8, that is 16, then plus 2 times 2y, that is 4y, is equaling to 10. So okay, this was 2x, sorry, and also this is 2x, so meaning this is 4x. So x plus 4x, that is 5x to be equaling to 10 minus 16, 10 minus 16, okay, simply this was a minus, this is a minus 4x, meaning we shall have, we shall have x minus 4x, which is negative 3x, to be equaling to this is 10 minus 6, that is negative 6. So simply our x is equaling to 2. Now after getting x is equaling to 2, I don't know whether you people are following, then our y in this aspect will be equaling to 8 minus 2 into 2, meaning our y is 8 minus 2 times 2, which is 4. Our y is equal to 4. So meaning this point down here is 2, because x we got 2, and this point our y is 4. So the coordinates is 2 on x-axis and 4 on y-axis. Then we also have this point C. Point C, we have coordinates. At this point, remember we have got x-axis 10 and y-axis 0. So to know the optimum point, we need to substitute each of these coordinates into our objective function, which is minimize cost, and we see which of those three gives us the minimum cost. So we can introduce another slide here. Okay, we can introduce another slide here, and okay. Can introduce another slide. Okay. Can introduce another slide a little bit and come here. So here we have our points. Point A, which was 0, 8. We have our point B, which we have written as 2, 4. And have point C, which has been 10, 0. So we need to substitute these points in our objective function. So in this aspect, we need to substitute all of this in our objective function. Remember our, okay, if I can draw here, our objective function was 5x plus 7y. Then for point A, our cost, I can call it as total cost, will be equaling to 5 times 0, because our on point A it is 0.8, then plus 7 times the units of y, which is 8. We shall get a total cost of 7, this is 0 plus 7 times 8, which is 50.66 US dollars. Then for point B, the total cost will be equaling to 5 times what is the value of x is 2, then plus 7 times the value of y is 4. So what do we get? This is 5 times 2, which is 10, 7 times 4, 28, 10 plus 28, that is 38 US dollars, 38. Then on point C, total cost is equaling to, what is the value of it will be 5 times 10, then plus 7 times 0, because the value of y is 0 in that aspect, which is 5 times 10, 50 plus 0, which is US dollars 50. So now, because the objective function is to minimize cost, which of these three coordinates or these three quantities are giving us the minimum cost? 56, 38, 50. Of course, this is the minimum cost. So these two units which used for point B will be the optimum point. So the optimum points or points that will minimize cost as our objective function, it will be the x will be 2 and y will be 4, and this were on point B here. If you can go back, it was point B. At this point, that's where the costs are minimized. Thank you. If the problem was maximizing profits or revenue, in this aspect we would choose the highest profit if these were profits. In this aspect, this 56 would give us more profits than this point. So to go for 0 for x and 8 for y. But because our objective function is minimizing cost, that's why we are going for point B, which is giving us a minimum cost of 38. Thank you.